All right, guys. Continuation of talking about using the calculator to find numerical derivatives. I want to show you one example to show you that, in fact, your numerical derivative, your approximation, gives you a pretty accurate value. And I want to show you one example of how you can be fooled. So you need to be a little bit careful. As with anything in math, you should know what you're doing before you actually do the calculations, so that you can look at your calculations and say, well, that doesn't make any sense. Examples from my geometry classes, when people calculate that the side of a triangle is negative, and then they write it down and they turn it in. It's like, what were you thinking? So very quickly, the actual definition of derivative here, we've got the limit as h goes to 0 of x plus h cubed minus x cubed. The function we're looking at is f of x equals x cubed, and I want to find the derivative at x equals 2. So if we're thinking about what's happening here, I am expecting some decently large positive number. So let's do the algebra. Here we go. The algebra says this is the limit as h goes to 0. Well, I'm going to use a binomial expansion. If you're not familiar with that, look up Pascal's triangle and binomial expansion. But I don't have to multiply that all together. I know that that is x cubed plus 3x squared h plus 3xh squared plus h cubed. And hopefully you see that pattern. Notice it's 1, 3, 3, 1, and the powers are changing by 1 each time. I've got a minus x cubed on the end, and it's all divided by h. X cubed minus x cubed, those cancel each other out, and I'm left with the limit as h goes to 0 of, and I'm just going to do some algebra here. Notice that I could factor out one of the h's and then reduce those to a 1. And so I'm left with 3x squared plus 3xh plus h squared. And of course, as h goes to 0, those become 0. So this becomes 3x squared. The derivative of x cubed is 3x squared. Now, I was asked specifically for the derivative of x at 2. The derivative of x cubed at 2, and so that's going to be 12. All right, let's look at the approximation. Well, the approximation is 2.001 cubed minus 1.999 cubed divided by 0.002. And of course, where did those come from? 0.001 above the point I'm interested in, 0.001 below the point I'm interested in, and I'm doing the difference quotient on that. And when I type that into my calculator, I get 12.12345 zeros and a 1. Pretty darn close to 12. Now, let's confirm that that's exactly what the calculator is doing, or at least suggest that that's exactly what the calculator is doing. If I type in math 8 into my calculator, I will either get this or this, the first one or the second one, depending on what operating system you're running. The derivative with respect to x of x cubed at x equals 2 is how you read the first one. And the second one, you're taking the numerical derivative of x cubed at x equals 2. And when you do that, what you get is 5 zeros and a 1. So again, approximately 12. Now, I did say that we need to be a little bit careful, because what if I'm looking at the function f of x equals absolute value of x? Well, I already know that it is not differentiable at x equals 0. So if I am asked to find f prime of 0, and I go into my calculator and I type in the numerical derivative of absolute x at x equals 0, it will say that this is equal to 0. Why is that? Well, very quickly, if I go 0.001 above and 0.001 below, you see the problem there? If I take the absolute value of this minus the absolute value of that, all divided by 0.001, 0, 2, I get 0. So this, again, another example of why it is so important that you already have an idea of what your answer should be. You should know, looking at this function, that it's not differentiable at that corner, so that you're not fooled into typing stuff into your calculator and saying, oh, derivative is 0. Moving on to the next problem. All right. Why don't you do, for my classes, go ahead and do exercise 23 in the book, and I'll see you in a few minutes. Actually, whoa, take it back. Do 17 and 23, and then I'll see you in a few minutes.